Okay, I'm not a PC user, so I have a problem here. Here you go. All right. Good afternoon, everybody. My name is Sveinung, Loekken. I work in the Directorate of Earth Observation Programs here at ESA. And I'm here to present the ESA Helix Nebula Flagship, which is the SuperSites exploitation platform. I'm going to give you a little bit of a description of the project, the status of the project, because we haven't completed yet. We still have almost a year to go, and what our planning is. This presentation, just to give credit where it's due, was done essentially by Jordi Fares, Francesco Casu, and Wolfgang Lengert, with a small contribution of myself, which is why I get punished and have to stand here and talk to you. Okay, so let's start. This is what we're addressing, and you know the general context. There is no reason to dwell on fourth paradigm, or data exploitation in general. We're talking about big data. We're talking about processes where we take big data sets and heterogeneous data sets, and we try to translate it into something that is useful. So information that is either actionable or that have some added value to it. In SEP in particular, what we are looking at is a field of geohazards. So we're talking about volcanoes, we're talking about earthquakes. This has popped up in the context of something which is called GEO, and the Group on Earth Observation is one of the main forums for Earth observation activity in the world. It is an intergovernmental voluntary organization with lots of members, and with the overarching objective of creating a global Earth observation system of systems. In this context, what is very important is access to data, that the people that do work that add value to Earth observation data have access to data. And therefore, GEO has defined a set of data sharing principles which exactly go in the direction of open and free data access for all scientific use. This is fundamental for us. Within this context, a few years ago, and before the SEP started, on a task from GEO, the Geohazard SuperSites was created. The objective was essentially to address some of the social benefit areas that are important to GEO, and in this particular case, to better understand the geophysical processes causing geohazards such as earthquakes and, oops, I think I'm on automatic here, earthquakes and volcanoes. Essentially what it is a global partnership of scientists and of data providers, both satellite and in situ. What's really important there really is that it brought together a community that has a common need and a common objective, and the data that is required by that community. The overarching objective of the SuperSites were the Geohazard SuperSites, which is still existing. You can see the partners on the right-hand side. It's essentially to support national authorities and policymakers in both risk assessment and mitigation strategies for what regards geohazards. In this context, it has a follow-on, the SEP, so this is the flagship I'm talking about now, was defined and put into Helix, or implemented in Helix Nebula. It's essentially a proof of concept for what is a natural evolution of the Geohazard SuperSites. If you think about it, the SuperSites brought together a community, and it brought together the data that community needs. When the data starts getting really, really, really big, it's not enough that you go to a web server or to an archive and you pick it up, because maybe you won't be able to transport it, and probably you won't be able to, you probably at home don't have the processing power to deal with it either. So essentially what SEP is, what it is essentially an e-infrastructure where you, in addition to the data that this community needs, you also put the tools on there, and you put the resources that is required for processing. That means what you essentially do, in addition to giving access to data, is you give the place where the work is done. This is what we refer to as an exploitation platform. In the SEP, we will have up to, I say, it's in parentheses, because right now the application inside Helix Nebula or inside SEP, we only have ESA data. So we're looking at 20 years of ERS 1 and 2 SAR and 20 years of ENVISAT ASAR data. But we aim in the next phase of the project to try to put in as much as possible of the data that was already in the supersites. So we're looking at up to 100 terabytes, and we're looking at a time period of around 20 years of Earth observations. Obviously, there is a scale difference. We just saw from Rupert's presentation at I think he was talking about petabytes a week or something. So there is a difference of scale which is pretty evident when you think about it. But you have to extend the context a little bit, because here we are in a particular application context which has a slightly different volume than what you would typically find in high energy physics, for example. The output of this exploitation platform, so the things that come out of the processing we do, what is actually the value added, is displacement maps, it's subsidence measurements, it's stress assessments, and it's support to modeling. One of the test cases that we are implementing is the CNR SPAS processing. So CNR is the Centro Nazionale delle Ricerche in Italia, in Italy, and SPAS has a number of application areas. Basically, this particular processor or application, it takes stacks of satellite images, so in this case either ERS or NVSAT, and well, actually from this one it looks a bit like we are in the process of blowing up people's workstations. That's not the intention of this at all, okay? The problem here is essentially that to generate each of these maps you have a sequential processing time of 300 hours, which is long under any kind of definition. Here's an example of what you get out, so you can get an idea for what SPAS does. This is a subsidence map of Rome, and you can see the movement. Wherever it's green means that the buildings and buildings and infrastructure is essentially standing still. Where it's red, like down here, which is actually where my house is, it means that it's close to the river. And I would like to, you could have sent me this a couple of years ago if you don't mind that. Here you see the red one, so that is actually moving up to a centimeter a year. In this case it's sinking, which is even worse from a viewpoint than if it's growing. Incidentally, and courtesy of CNR, you are right here, and we are safe. This building hasn't moved. This meeting room has been standing still for the last 10 years, and I see that as a very positive. Now, this is what we're looking at. So we came from this workstation blowing up at CNR, and this one looks much more friendly, okay? So nothing is blowing up, and the basic idea, the scenario that we're looking at in SEP, the problem we're trying to solve is the 300 hours to put the processing on the cloud instead of on somebody's workstation, which cannot obviously handle it. The solution we have defined, so this is basically the IT solution that lies behind SEP. It has 5 major components. The first is to provide infrastructure as a service, so that's the computing power, the storage and the network, from different cloud providers in something called a hybrid multi-sourced cloud. And that means, first of all, that you have more than one provider, and second of all, that part of the cloud where you will be putting your data and doing your processing is private, so it's under ESA control in this particular case. The reason we do this is to try to get as many permutations of possible architectural setups as we can. Second objective is to allow users to search and access data at high performance, and to allow data providers to upload data. Both of these are fundamental functionalities, obviously. We also want to allow users to process data on dedicated sandboxes. That means places where you do the algorithm development and small data processing for testing, for example. Then we also want, obviously, and this is the raison d'être, the core, the fulcrum of the activities, to give access to large data processing. And all of this we want to integrate into a nice common security framework. I'm going to tell you now essentially what the status of these various objectives are. So the first one is the IaaS resources, and there we've done the proof of concept with the Atos Cloud Sigma and Interroute. It's worked out just nicely. We've done the API integration with T-Systems, and those of you who are not so familiar with IT Argo, this means essentially that the application layer is integrated on one cloud provider. And we've done the deployment of a small private cloud here at ESA, which we are operating and which we're using. We still have a couple of things to do. We have to do the API integration with other cloud suppliers, and we have to make use of the federation layer. I think those of you who were here this morning, you know a lot about it, and there's no need to dwell on the details. Second objective, so to download, allow scientists to download and to access data at high performance, and then data providers to upload the data. And there what we've done is to, we've moved all ESA supersite data onto the platform as 13 terabytes. And we've made all of that data available. We still have to announce the supersites, not to the old GeoHazard supersite users. We have to announce the availability of the service, and in the next phase of this project, we have to try to get the data from the other players in as well. Here's the user interface, and it looks disarmingly simple. And maybe we should talk, Rupert, on the user interface design. I mean, seeing the thing that you had made, which was very nice, by the way. Essentially, this allows you, it gives you access to the data, and it also allows you, through this interface, which is not well explained here, but it allows you to provision the data as well. So you can upload data. You can actually deploy through the interface new data centers or chunks of data on the various cloud providers, and that's not well described here, but that's the significance of this. Point 3 is to set up the sandboxes, and we have deployed one at CNR. Cloudification of ESPA, so that is the application layer for the processing that the CNR is doing. Cloudification, I realize it's not a word, but I'm willing to take a bet with somebody that it's going to be in a few years, so we're going to be using it anyway. We made ESPAS, the ESPAS application, possible to use on the cloud, and we are running it now on the cloud. Gamma is something I'm not covering here. It's another application layer for this kind of processing, and we have other test cases there that I won't be going into detail on, but we got the software licenses set up for the cloud for this particular application. What we still have to do is the qualification, so we have to, it's almost a formality, but we have to somehow make sure that what we did, even though, I mean, we see it starting, we see it running, and we see it completing, we would like to have a mathematical certainty then that what comes out at the other end is correct. So we have to test it, we have to qualify it, we have to test it very carefully. Then what we have to do is to deploy the sandbox solution to users beyond CNR who are now using it. Okay, here's an example, and I start to see a pattern here, actually CNR, because this was where the last meeting was here, and they actually set up the same kind of thing, and I guess you were able to prove that you were safe as well at CERN in July. This was before the project started. The processing done, not sequentially, but done on the Amazon cloud, so not in the context of SEP and not in the context of the Helix Nebula. And this shows a significant increase in, or improvement in performance, obviously. So what we have to do is to make sure that we are able to meet this kind of performance target also in Helix Nebula and also in SEP, and we have been able to do that. Okay, here's another example. Well, this is what has happened now. So this is a processing of the Napoli Bay Area, which, by the way, you can see that it's a famously unstable area, and you can see that on the subsidence that there is movement there. This is processing that's done on SEP, and the numbers between the two is not there. They're not normalized. So here we're talking about a different number of nodes, different number of images, but they are comparable. So we are looking at the solution we've set up in SEP. It actually works, and it works to the level that you would expect comparing with things like Amazon. Okay. Okay, so large data processing, and here we come into the really important stuff. We have we've completed the large data, the large provisioning during phase 1 with Cloud Sigma, with Atos and Interroot, so we can deploy and run huge processing on these providers. We've also set up the dynamic provisioning, so that is the provisioning where you don't need an operator to sit down and start a machine, but that can actually be deployed through the application itself. We've tested that with T-Systems. This is very interesting, and I think it's very important, but because it makes it possible to run huge processing scenarios without having 15 people sitting and deploying and taking down machines for you. What we still have to do is to qualify it. Again, we have to test it very carefully. We have to deploy on a second cloud provider, and then we have to do the deployment over the whole Helix Nebula cloud using the federated IPI, which I'm sure you've been told about. This is the target processing scenario. So here we come from this one. Okay. We come from this one to from a 300-hour processing scenario down to a scaled one, because the importance here is that we have different use scenarios, and there are scenarios where the processing needs to be extremely rapid. Emergency scenarios, CNR is a provider for the civil defense here in Italy as well. And you have obviously processing that has less urgency, in which case you're looking for routine, or you have looking at kind of a routine scenario. The routine scenarios, our target is to get the 150 images processed in 48 hours, which is still one order of magnitude below what we had in sequential processing. And in an emergency scenario, to get the value-added product out in 12 hours, which is a strict and a difficult target to meet, but we think this is going to be perfectly possible in the context even of this project. Okay, last objective was to nicely integrate with the common security framework, and what we've done there is to put secure access on the data via ESA single sign-on system. It's basically a system that's implemented on a standard suite of security integration. And we've implemented that for Interroot. This is also securing the processing on demand, so you shouldn't be able to hack it, and it gives a level of security which is fundamental, because starting a job, starting a set of jobs, starting processing has a cost. So it is that's one thing. The second thing is that we're looking at scenarios where data is proprietary, where algorithms are proprietary, where there's IPR in all kinds of places potentially. So I see this as a very important point. What we need to do is to extend this solution to the other cloud providers, essentially. Okay, and that's for the progress of the project. The last time we saw each other, so that was in Geneva in July. We were on the first triangle here. So we were doing the assessment of the cloud provider. We've done the transfer in phase 2, and we're closing it this month. I think we're only 1 month late, and the phase has been successful. The outcome has been not surprising, because in the end, we call it a proof of concept, but anybody here who uses Gmail is on the cloud. You're on the cloud when you read your email. It's not a miracle that this works. I mean, it's not a surprise. It would be a surprise if it didn't, I would say. So it's worked out fine so far. Now we're coming into phase 3, and that has essentially 3 objectives, or 3 work packages. The first is to do a continuous service provision from here on out. Now we got it up and running. In the more or less in the midterm, so 6 to 9 months from now, we're going to be looking at the multi-sourcing and the integration in the federated part of Helix Nebula, which is going to be interesting, and where I'm sure we're going to have maybe more of a technical challenge than what we've had so far. We're going to be doing some enhancements, so we're going to look at application enhancements and service enhancements that make the basic technology, the basic application, the basic functions easier to use, better, etc. And what for me is the most important is the exploitation and demonstration, and the target there is to try and actually activate the user community, because in the end, none of this is going to work for anybody if we don't have the users there. We built the stadium, and now we would like the audience to come. And I think that is a task that is not to be underestimated. We are starting in a good position because there was already a super sites, a geohazard super sites done by Geo, even though with much less functionality, etc. in it. So we're starting with an advantage because we're not starting from scratch and we have to start calling people that never heard about it before. But still, this is a new concept. It is a new model of work. It is a new business model even. So there is some work to be done in dragging on board and activating, getting activity, getting buy-in in the short term and also in the long term from our user community. So that is the third part here. The objectives of so next steps and objectives over the next year is to open the data access to the scientific community. It is to complete and deploy the application layer. So that is what is actually useful, the useful functionality that the user community gets from SEP. We have to benchmark the federation layer and then adopt it. And as I said, this is probably going to be a technical challenge, in my view, over the next year or so. And it's the promotion of Helix Nebula and especially the super sites exploitation platform in the user communities I just mentioned. And there we have the data hub, the processing on demand, the user hosting, and the deployment of user services. And that's basically it. Back to this one, we have, and I should have mentioned that actually, the project ends at 18 months. So at 18 months, because this is an engineering project, we don't have a phase of, well, I mean, the third phase is a matter of also service, or it's pre-operational services almost. But there is no plan so far for what happens after the 18 months, and this is something that we're looking very much forward to discussing with a lot of people, especially based on the results that I'm personally convinced that we will be able to show after phase 3 completes. And that's all. Thank you very much. Thank you very much indeed.